So remember, a transformer does not change what? Power. Power in should equal power out. Of course, power out's going to always be a little less than power in because there's no such thing as a transformer that's 100% efficient. I can't get my selection where it's going to record sound, so let's see if y'all can hear this. If it can't, we just won't quit. Not don't look like my sound's working. So what we're going to do with transformers, of course, is transform AC voltage from one to the other. They do not generate power, they transfer power from one AC circuit to another using magnetic coupling. So sometimes we use transformers for isolation. I'm going to have to make sure I stay over here because my headset went dead. It works on the principle of magnetic induction, right? So AC generates, this is why AC works, because AC changes. So AC automatically creates a change in magnetic field, right? So we have motion. We have one coil of wire, then we send that motion to another coil of wire and inducing the voltage into the other set of wires. So we have two sets of windings. We have a core to concentrate the magnetic field. We have a secondary winding. The secondary windings always point toward the load. And then your primary windings are going to point toward the source. Even if we went through multiple transformers. The primary side always points back toward the source, and your secondary actually points toward the load. Are we okay? So, schematic symbol for a transformer. A lot of people leave out the core. Now, notice the core is drawn in stripes. It's not drawn into one solid piece, and we'll look at that why that is in a minute. So, this is a symbol for a basic symbol for a transformer. Sometimes they'll vary the size of the windings to let you know if, so sometimes you'll see this. So if I ever see this, I know this is a step-down transformer. If I ever see this, I know it's a step-up transformer where the primary has more turns than the secondary. If it's drawn like this, I don't know. It's just easier to draw. Are we okay? Three main parts. We have a primary, a coil, or primary winding, and all it is round around a piece of metal that we call the core. The core's got one function, and that's to make sure that the magnetic field that's being generated in the primary is coupled to the secondary, right? Because the strength of the magnetic field would determine how efficient the transformer is. Secondary winding is an electrical wire wrapped around a laminated metal core shared with the primary of the output side. The core is a ferrous metal, right, which is a metal that can concentrate a field. So we wouldn't use aluminum for a core. This is usually iron, usually made out of iron. Can conduct magnetic field through it, and of course iron is used a lot. Now what we do, the problem we have with this core is a chunk of metal. And what do we need to induce a voltage? We got to have a conductor. So what happens if we just take a chunk of metal and wrap that magnetic field and try to transfer the field through it, it's going to induce a voltage and a current into the core. These are called eddy currents. These are undesirable currents. So what we do is we take the core and we split it up into hundreds of small little circuits. And here the currents cannot combine. So even though there's current in this lamination cannot add to that lamination, cannot add to that lamination. So now the core becomes a lot more efficient. And you can actually see these. I'm going to pass this around. So this is, normally you can't see the coils anymore, especially on industrial transformers, because the insulation on the windings are very, very thin, right? So they can get really good coupling out there on magnetic coupling. We're right past it. Like I said, I don't know if we're going to be able to focus this in. So you can't see the windings anymore, but you can definitely see the lamination. Can y'all see the little stripes there? So each one of these is another set, and what it does is the voltage and the current being induced in this one will not combine with that one, will not combine with that one. So they're coated with a real thin coating of insulating paint. And we do that. So you can tell something that's designed around AC right off the bat because it's going to have laminations on it. It's going to use laminations if it's going to use to concentrate a magnetic field. There you go, Lane. And I want you to look on there. This is rated at 0.075, but it's not rated at watts. It's rated at 0.075 kilowatts, or kiloVA, excuse me, volt amperes. So power supplies or transformers are rated to transfer what we call apparent power, which is, this is the power that's appeared to need to run the load, right? But because of this phase shift, apparent power, if you don't correct it somehow, apparent power will also always be greater than what we call true power or real power. So transformers are not rated in watts, they're rated in what? Something called volt amperes. I went past it. Oh, I'm sorry. I gotta get out of this port. Let's get back here. Since the core is technically a conductor, current called eddy currents will be induced into the core, just like the transformer in the secondary. The currents will be very large due to the size of the core and to make the transformer very inefficient. To prevent this from happening, the core is split into individual little laminated plates, very thin plates colored with a lamination that are isolated from each other. So now these little currents can't do what? They can't combine. So when you look at an AC relay, you'll see that it uses laminations. So the laminations are used to act to concentrate a magnetic field and not be a conductor, right? Does that make sense? So this is a transformer. Here, the most electronic transformers, industry transformers, especially small ones, the actual wires are going to be inside some type of plastic enclosure. Because of that, I showed y'all magnetic wire last class, right? Very, very thin insulation. And if you come by and you accidentally nick that stuff, then what would happen? Then now you're going to short out some of your windings, and you'll change the ratio of your voltages. So basically the way we do it, we have a primary. It's got a change in magnetic field, right? It induces, it generates a magnetic field. The magnetic field is coupled over here to the primary. So the magnetic field will cut these windings, would induce a voltage over here through induction, right? Just like me doing what? Swinging that wire over here. But here the magnetic field is being produced by electromagnetic induction. Now, what determines the amount? What determines the amount? The strength of the magnetic field. The number of conductor loops. And then the last one would be the speed of the motion. Speed, Rich. Now, of course, we can't control the speed of the motion because Alabama Power does 60 cycles per second, right? So if we took a transformer that was designed over here and we took it over to Europe, we wouldn't get the same voltage out of it because they use what? Yeah. Now, so what we're dealing with here is this guy right here, the number of conductor loops. Now, it works out to be the number of conductor loops of the primary compared to the secondary. So if the primary has 2 loops for every 1 loop over here, so if that's got 100 loops over here, this would have 50 loops, then this transformer would divide by 2. So how much voltage you get out of your secondary depends on the ratio between the what? Between the loops in the primary and the loops in the secondary. If the loops in the secondary are less, then the transformer is going to step the voltage down. If the loops in the secondary are more, then it's going to do what? Step the voltage up. So that's one thing we need to know. That's what they give you. They'll either give you the input voltage and the output voltage. Like here, we're going to take 208 and we're going to drop it down to around 120. So our transformers are going to step down. So these little black boxes you see, you come out and you see the disconnect, the gray boxes. We're going to be on the white panels, running up to the transformer. And once we wire the transformer, we're going to leave it there the whole semester. So this transformer here, we'll look at in a minute. We can wire this transformer either to divide by 4 or divide by 2. And this is very popular in industry because industry usually has at least 2 different voltage levels out there. One of the most popular voltage level in industry is 440. So what would the advantage of 440 have over 220? Less current to produce the what? To transfer the power. So in industry, they're going to have a lot higher voltage levels. Well, instead of if I've got 440 and 240, and I need to get 120, it would be nice for me to carry one transformer that I can wire to divide by 4 and divide by 2, than having to carry 2 transformers, right? So you'll see a lot of transformers in industry that will actually step the voltage up or step the voltage down, and you wire it depending on what you want the division ratio to be. But the division ratios are set, the ratios are set, right? An electrical transformer normally consists of a ferrous laminated core and 2 sets of windings. It works off what we call mutual induction because we have everything we need. We send current through the primary, which creates a magnetic field. Then that magnetic field cuts the secondary, and we have everything we need to induce a voltage or an EMF into the secondary, right? We refer to this as mutual induction. So we're inducing the voltage into the secondary. And what's nice is that the secondary is totally isolated from the primary. So this is why out there on your power lines, if you've got a transformer out there, they have to run a ground down from that transformer to reestablish ground. Because if they didn't, the ground on this side wouldn't necessarily have to be the ground on that side, right? Or the common on the left would not have to be the common on the right. So a lot of the power that they transmit, they use a delta transmission, and it's not even referenced to ground. So we'll talk about the advantage of delta over Y. Got to have, of course, we already know this, right? Everybody okay with this? This looks like a good test question, right? So what do we need to induce a voltage? Got to have a what? Magnetic field, got to have a what? Conductor, got to have a voltage. What determines the amount? Strength of the field. This is what this is what your transformer uses. The strength of the field is determined by the current requirements of the load. So in a transformer, the current requirements is set by the load. And the speed of the motion. We don't do anything with the speed of the motion because wherever you live at, it's going to be changing at a certain rate. And of course, here on the United States, what's our frequency? 60 hertz. So what we do on a transformer is we do this. So if I took a transformer here and I took it over to Europe, the division ratios would be different, right? You understand? Because why do they change? There's a lot of math involved to calculate the speed, the field. One is the size of the wire. So the gauge of the wire determines how much current we can get out of it. So if you ever look at a transformer, I'll try to bring one up here. If it's a step-down transformer, your primary is going to use real thin wire, and your secondary would use bigger wire because usually the secondary current's got to be what? It's going to be more, right? So a lot of times you can actually, if you can see the windings, you can actually tell the primary and the secondary. Sometimes it's hard because a lot of times they just wind them on top of each other. Mutual induction. So we know that all we got to do is have something that allows a really good coupling between the primary and secondary, and that's where this laminated core comes into place. So it concentrates that magnetic field between the primary and the secondary, right? You understand that? In lamination, because the core itself is basically a conductor, and we would induce a voltage and a current into it unless we can break that current, create a bunch of open circuits, right? You understand that? So that's why we require that laminated core. Don't need to know that. So operation, we come up here, we attach a load to the secondary. It's going to require a current. When it requires a current, it's going to require more strength of the magnetic field's got to go up. This is going to provide that. Put power in and power out. So if this guy needed 100 watts, how much would your AC source have to provide? If my load needed 100 watts, how many watts would my AC source have to provide? 100 watts. Transformers don't change power. I think I told you about the guy from Birmingham when we made the job available. We had interviews, and one of the things he decided, and they were supposed to do a lecture. This guy decided to lecture on transformers. And guess what he said? He said it steps the power up or down. Guess what he didn't get? He didn't get the job. Because anybody that does not know, we cannot create power. All we can do is take power and change its form, right? You understand that? Power out will always be less than power in. There's no such thing. No matter what you see on YouTube, no matter what you see, I saw a video on YouTube where a guy hooked a generator up to a motor, and then he unplugged both of them, and the motor kept running. So he was saying the generator put out enough more power than what's required to run the motor. And I knew right off the bat it was wrong. So no matter what you see, no matter how convincing it looks, and they can do a lot of tricks to fool you, we never have anything that's 100% efficiency. We had a guy come in here and he says, I got a great idea, Rich. He says, we've got these electric forklifts at my business. I'm going to put a generator on the wheels. And when the forklift is running, it's going to charge the battery. And I said, your batteries are going to run that faster. Because now it's not only got to support the watts to run the watt. It's got to support the watts to run the generator. Right? You ever notice when you turn your air conditioner on, your motor tries to go down? Why? Because that generator has got to produce actually more watts than what you're using. You'll understand that. So if you get 100 watts over here, your motor's got to provide what? 100 watts or a little more. So no matter what you see, guys, no matter how convincing it is, there is no. We had a guy and he actually put a patent on it. He figured that he could put a motor that if it did a stroke this way, the motor would actually come up and pick itself up off the ground, and he can move it just by the motor. Something in motion wants to remain. So that would be like a sailboat moving without any water, air. No matter what you see. And they're really convincing. They look really convincing. But they're just there to make you look like a lot. If you get into people that know, and they look very convincing, and you go out and you spend all this money, and you build it and it don't work, and then the joke is on you. We never, ever, ever can do what? Get more power out than we put in. Never. So, never. So this is a transform action. Notice that when the magnetic field goes out of here, current flows this direction, and no, this is not right. And current flow over here is in the opposite direction. So here it's coming out, here it's doing what? In. So what happens on a transformer is that if we hook them up exactly the same, then the output will be 180 degrees out of phase from the input, which usually means nothing to us, right? So what they'll do on some transformers is they'll put dots on them, which saying if your output phase needs to be in the input phase, then these are the ones you need to use for L1. You need to use both these for L1. And sometimes they literally wire the secondary in reverse of the primary. And that way the output and input would be out of phase. But it don't make any difference because the phases are totally isolated from each other, right? You understand that? So the phase in your house might be 180 degrees out of the phase of your power company, but it makes no difference because you only see the phase that you get. Does that make sense? So this is basically the way a transformer works. So what's the core for? To couple the magnetic field from the primary to the what? Secondary. And why is it laminated? Because what it does, it breaks it up into a bunch of open circuits, right? You understand? And that big old core don't combine and become very hot and become very, very inefficient. Like this right here. Turns ratio, we already talked about that. What determines the output and the input? It's the ratio between the what? The primary and the secondary. So if the secondary has less turns than the primary, the transformer will do what? Step down. If the secondary has more than the primary, steps up. Some transformers, depends on the insulation. Some transformers you can hook it either way. And you can either hook it up, step up, or step down. That all depends on. Some you have to be real careful for because the insulation on the core might not work for to make a transformer that's normally used as a step down and use it to step up. You understand what we're saying? So if I just wire what we used to call the secondary, if I use that as my primary, and then I use my secondary as my what was originally the primary, I use that as my secondary, then it will step both together. Some transformers allow you to do that. This is why industrial transformers, the terminals on the primary are labeled with X's. I mean on the secondary, they don't use S. And on a step up, I'm sorry, the low voltage side is labeled with X's, and the high voltage side is labeled with H's. And this is the way the terminals will be labeled. So if I wanted to step down, I would bring my voltage in on the high voltage and take it off the low voltage. If I wanted to step it up, I would go backwards, right? Everybody okay? So this is standard in industry. So the low voltage terminals are going to be labeled with what? X, and your high voltage is going to be labeled H's. And we'll see that on our transformer. And here, this is a pretty good animation. So here they're not changing the turns ratio on the primary. They're changing the turns ratio on the secondary. So we can buy transformers to step up. We can buy them step down. And like I said, some of them. But one thing you can't do, you can't rewire it, right? Understand? We can have multiple windings, and we can change the turns ratio by the way we connect the windings on the transformer. But as far as us setting what we want, we can't do that. So we have a divide by 4, divide by 2. So what we have is we have jumpers that we can put on it to change the turns ratio on either the primary or the secondary. We're changing the turns ratio on the primary. So here's the formula: number of turns on the primary divided by the number of turns on the secondary. This gives you the ratio. So sometimes it's a fraction. If your primary is smaller than your secondary, you'll come up with a fraction. And if you know the turns ratio, you just take the voltage you apply to the primary, you multiply it by the turns ratio, and this would give you your secondary voltage, or approximate secondary voltage. This makes sense? Everybody okay so far? Any questions? So normally they give you that. They'll say it's a divide by 2, divide by 2, divide by 4. So that's what we've got. So technically we could bring 480 in here, and if you divide 480 by 4, what will you get out of it? 120. Or we can bring 240 into it and divide it by 2, and we still get what? 120. But what we do is we rewire the transformer. You can see this. This is a dual voltage transformer, and normally what they'll come, we're going to do it manually. So we're going to use dumpers on our transformer. And I didn't want to do that. I don't want to do that. So most of these dual voltage transformers, if it focuses in, will come with these metal jumpers right here. And what you can do is you can move them to get the division ratio that you want. This is a divide by 6, divide by, I don't know. So it's set up for 120 on this, and it's wired to give us what? 24 volts on the output. So normally a dual voltage transformer will come with these. So you can move them around depending on what ratio you want your transformer to work at. Here we have 2 ratios. This is 440 down to 24, or 120 down to 24. So this would be, we could wire this as a divide by 6 or a divide by 12, right? Everybody understand that? Okay. We're going to actually jump ours on the side. You can actually see this transformer over here on the right. You can see the jumpers on the top, and that's what they've done. They've got this thing wired to divide by 4. I'm sorry, divide by 2. Everybody, we call them step up, step down transformers. Does that make sense? So step up transformer means we get more voltage out than we get on the primary. The secondary voltage is higher than the primary voltage. Step down means the secondary voltage will be less than the primary voltage. And like I said, industrial transformers, they don't rate them as secondary and primary. You have a high side and you have a low side. And you can wire it to do what? Step up or step down. And how do we identify the low side? Those terminals are going to be labeled with what? X. High sides are going to be labeled with H's. And these are all the same thing. We can calculate the turns ratio by measuring the output voltage, right? Divide that by the input into the input voltage. That would give us the turns ratio. But normally and we might do this if I've got a transformer and I don't know what it is, right? You understand? So I might come up, even if it's rated at 1,000 volts, you can still hook it up to 120, right? You understand that? Then measure your secondary, and you can take what you measure on the secondary, what you have on the primary, and that would tell you the turns ratio. And then all you're concerned with, if you don't know the voltage, you got to be careful on that, because if you put too much voltage on there, it might exceed the rating of the insulation on your conductor. And if something, and one of the big things that happens is these dang conductors, the insulation is almost nothing, right? You understand? So just the vibration. So AC, when you come over here, you have these 2 transformer windings. This guy's putting out a positive. This guy's getting a negative. What does the windings want to do? They want to move toward each other, right? You understand? And the windings, positive, the windings want to pull together. So this is why transformers hum. Transformers hum because the windings are constantly trying to do what? Move in and out with each other. So what they do is they clamp them things down. You ever see these transformers? They'll be dipped in lacquer to do what? To try to seal those conductors so they don't do what? They don't move. And what happens if they do move, then they're going to rub against each other. They're going to do what? They're going to peel off that insulation. Then you're going to have shorting windings. And then what happens is your turns ratios change. So normally if you're not getting the output voltage you expect, it's because you have shorted windings inside there. By the way, these guys have a lot of wire. They have a lot of resistance. And you can, if you got a transformer and you have all the same transformers, you could get your own meter and record the primary resistance and the secondary resistance somewhere, and you can check them with an ohm meter after that. So that's basically what we do. We've got a good transformer. We measured that, and we've got a transformer that's not working. We just measure the ohm values, and we can tell if the ohm value is a lot less, it means it's got shorted windings in it, right? Motors do the same thing, guys. Motors use that magnetic wire, and that's the biggest thing they have is the vibration and these insulation rubbing against each other and doing what? And then you have shorted windings inside there. And why is the insulation so thin? Because they got to get really good magnetic coupling between the wires, right? So we call it magnetic wire. So all this is just the same thing. We're going to go through this. So everybody okay at that, right? Okay. Transformer efficiency. No, there's no such thing as a perfectly efficient transformer. So power in and power out are not equal to each other. But for our point of view, we understand that, right? Understand. And like I said, most of our transformers now are about 95% efficient. So that means we'll have to put 5% more power into the secondary to get the primary to get what power we get out of secondary. So for demonstration and for calculations, we can assume these guys are pretty close to what? 100% efficient. Just so we can explain them. So transformers are between 95 to 98.5% efficient. So for this reason, we'll assume Alabama Power would really have to worry about power supply efficiency, right? Because they go through a lot of power, a lot of substations getting that from up there to down here. And every time you go through a transformer, you're going to lose a little efficiency, and you're going to have losses in the line. So even your power line, your transformer on your power usually has 3 taps on the primary side. So the guy that's wiring it can move it between 3 taps and get you close to 120 and 240. But actually, NEC says it's got to be within 10%, plus or minus 10%, and still be considered to be good, right? Does that make sense? So let's go back in transformer types. Control transformer. Control transformers, these are our low wattage transformers. These are not required to produce a lot of power. So what we've got what we call a control transformer here. It's rated at, now transformers are either rated in VA, they're not rated in watts, they're rated in VA, or they're rated in kVA, which is the 1,000 volt amperes. Our transformer is rated at 0.05 kVA. So that means it could actually conduct 75 volt amperes. Why is it not rated in watts? So we calculate watts by taking voltage times current. But they don't call this watts, they call it volt amperes. It's not called watts. Transformers are not rated in watts, they're rated in current and voltage. Your transformers have to apply apparent power. AC produces phase shifts, which means there's more power consumed than it's actually getting work on it. So all AC devices are going to be rated in volt amperes. And this is why Alabama Power wants you to have a really large power factor, moving toward 100%, because all their transformers, all their conductors has to handle apparent power. And what did I say they charge? They charge if you don't have a power factor over 95. If you have a power factor of less than 95%, you're going to pay a penalty in your industry, not you. Alabama Power takes care of the power factor at your house, right? So understand that. But big companies, they have to manage their power factor. So US Steel, like I said, they had one guy, one foreman out there, and that was his job. When I worked out there, we had all these mills that run. Our Alabama's power bill was over $1 million a month. And they produced a lot of their power. So all their blast furnaces, those produced the gas, they had their own power stations out there. Now they used the gases that were put out by making iron. They ran it through their boilers. They created their whole power plant, and their power bill was still $1 million a month. But that's running a power factor of 95%, right? You understand? If they got down below that, then their power bill would have went up. But Alabama Power don't like that. Why? Because all their equipment has to support that out-of-phase power. Out-of-phase power is not good for power grids. So that's why all these transformers are rated in VA. I think this one, which is used by the motor controls, this is rated at, it's on here somewhere, 50 VA volt amperes. The one we passed around, the one we're going to use is 0.75 VA, but it's in kVA. And you'll even see that a lot on TV. I talk about kVA. This is a transformer that we have. It's a dual voltage transformer. And this will be the only one. It's got bulky, this is the high side. We're going to use it as the primary. And notice the terminals are labeled with what? H, right? H1, H2, H3, H4. The secondary is rated in X1, and the low side is labeled in X1, X2, but we are going to use this for the low side. So what we're going to do is we're going to step down. Now, what people get confused with is why do they call it? So here's one winding. It's going to be between H1 and H2. The other winding is going to be between H3 and H4. And notice they have them crossed like that, and that's literally the way the transformer's wired. to bring this up. So when I look at the terminals on this transformer, if I can get it to focus in, let's try to drop it down some. Now this has a fuse, the secondary is fused. Ooh, that focus in real good. Oops. So here's the primary. So this screw right here would be, oh, got it upside down. Let me turn it on. The screw right here is H1. The next screw is what? H3. The next screw is what? H2 and H4. So H1 and H2 is on one winding, then H3 and H4 is the other winding. So notice this is the way we have to understand that to understand why they do it that way. So notice the numbers up here goes what? Goes H1, H3, H2, H4. So this terminal right here, these two terminals would be one of my coils, and then these two terminals right here would be, if you can see where I'm at, would be my other coil. Everybody okay? Yes, that's exactly right. So you caught that earlier. Good catch. So if I go down to a lower voltage, what does my current do to create that power? Yeah, so the lower the voltage, right, the more current's required. So that means if I want this thing to divide by 2, then I'm going to require less turns in my primary, but the current's going to go up in my primary. So what we do, if we're going to wire this thing to divide by 2, then what we're going to do is we want to hook the coils up in parallel. So what you do now, the current's divided between 2 windings, right? You understand? So how would we hook these in parallel? Well, I would want to take H4 and so you want these two connected together, so you want tops to tops and bottoms to bottoms. So I want to put a jumper between H1 and H3, and I want to put a jumper besides across H1 and H2. H2 and H4, excuse me. So what I've done is I've wired my primary like this. So now if I needed 2 amps, then this guy here is going to conduct 1 amp. This guy right here is going to conduct 1 amp, right? So for the lower the voltage, the more current we're going to require to put that primary. So a divide by 2 means what? I'm going to hook them in parallel. But notice the conductors are right beside each other. So that instead of me running big jumpers, then what I can do is I can, when I buy my transformers, it's going to come with these metal tabs. And now what I can do is I can just put these metal tabs between these things right here. So this is H1 this is H1 connected to H3. This is what? This is H2 connected to H4. But look what they can do. They can provide these jumpers, and I can just put those tabs on there, right? Instead of me running wires. So we're going to run wires on ours. So to get your low division ratio, we're going to hook the primaries up in parallel. To get the high ratio, right, you understand, we're going to hook them up in what? Series. Because now the primary voltage is going up, which means the current flow in the primary is going to go down, right? You understand that this is not Ohm's law. We're talking about the source. Now, you're right. On Ohm's law, if I put more voltage on a circuit, the current in the circuit goes up, but we're not talking about the load. We're talking about what we're doing with sources, right? You understand? The source. So on sources, the higher I can make the voltage, the less current's required to produce the power in the load. The power in the load, the voltage required by the load, requires what you got to do with your transformer. So if you've got a load rated at 120 volts, by George, you're going to have to set your transformer up to get what? 120 volts, right? You understand? So what we're dealing with a source, and the source is not dealing with voltage and current, even though it is in play. The source is dealing with how much power I've got to get out there to that load. And you got to get that power at a certain voltage, right? You understand that? So if I was going to set it for divide by 4, I would take one of these tabs off and I would put it right here between between H3, let's see, between H3 and H2. So let's draw it over here. So high voltage, I want to make more turns in my primary than I got in my secondary. So what I would do is I would hook these things in series. And if you get the terminal swapped up, you're going to cause problems. So I want this one hooked in series. So I want this one, I want the bottom of this one hooked to the top of that one. So I'd put a jumper right there. So that's why they cross these things, right? You understand that? So now instead of me running wires, I can get these little metal tabs and do what? Put it across the center 2 if I want to divide by 4, or put it across the outside if I want to divide by 2. This is the 12. So I'd put it across the center one if I wanted to divide by 12. I'd put it across the 2 outside if I wanted to divide by 6. Ours is going to be a divide by 4, divide by 2. And we're going to do it purposely. We're not going to change the voltage. The lab we set, and by the way, I'll show y'all when we get the lab. And one of the first labs we're going to do, and we're going to do labs next week, guys. So you need to have your lab book by what? By next week. The first lab we're going to do is we're going to inventory parts. And we'll probably try to do that this coming week. You don't need your lab book, because what I'll do, somebody in the lab, and I'm sorry, we'll probably do this next class. Somebody in the lab probably needs to have a book, because right now, a lab book, because when we inventory the parts, they give you pictures of the parts. So right now you don't know how to identify them. So what you're going to have to do is you're going to identify them by what? A picture. But we actually have a checkoff sheet. So the checkoff sheet can so if you don't have your lab book by Thursday, then you can look at my lab book for the pictures and then check them off when you find them, or you can look with your partner if your partner's got a lab book. We have to memorize this? What do you memorize what? We have to memorize the stuff that's in the lab book. We have to memorize the pictures and stuff. No, it's just. Oh, okay. Over time, it's just when we inventory them, because there's a lot of stuff we're going to go through. So when we first do our inventory, you don't know what a disconnect looks like. You don't know what a motor starter looks like. You don't know what this looks like. You don't know what that looks like. So the first lab, it has pictures. And then what you do is we have a check. You can check them off in your book, but it's hard for me to grade that. So what I do is I give you a checkoff sheet. So when you find the parts, you do what? You check it. Right, and make sure, because the parts in this lab has a tendency to move around. So when we teach the sensor class, sometimes the sensor people has to borrow some of the motor control stuff to do that. And what happens if you got something extra, we have a shelf back here, and we'll talk about that, where you take your extra parts and put them back there, and then the next group, if they're looking for something, they do what? And you don't steal parts. We've had that happen too. Where one team would finish their inventory and they would leave. The other team would go over there and they'd want to find something, and what would they do? They'd steal it off the other person. We don't do that. So if you find something extra, then what you'll do is there's a shelf back there. You can see it. So and what you want to do is you want to go back there and look first, and then we'll look at trainers that nobody's using and find our parts, and we'll get all the parts that's required. The second lab we're going to do is we're going to literally wire our transformer for different voltage levels. We're going to measure voltage levels inside the disconnect. So you need to make sure you have by next week, you need to have your what? Safety glasses and your gloves, right? You can just buy mechanics gloves. I think you can get mechanics gloves at Harbor Freight. They might sell them in the bookstore. It wouldn't surprise me. But Harbor Freight, you can get them for what? Less than $10, you know. You need those because we're working with lethal voltages. So anything above 50 volts, you have to do that. So are we okay? Okay. And we'll talk about the disconnect. We'll talk about what we're going to do, what's going to go on there, how to wire our transformer. Our transformer is a dual voltage transformer. It's a dual voltage primary transformer, which is this exact transformer right here. You can buy transformers with multiple windings. You can buy them. Like I'll try to bring the transformer in for our trainers, the trainers you'll be using. I think it's got 4 different secondary windings. because it's got a 12-volt power supply, it's got a 5-volt power supply, so it's got an individual winding on the secondary. So you get different division ratios that you don't even have to jump. You have all these wires coming out of the secondary. This is the transformer that we're going to be using. And what we're going to shoot for is we're going to shoot for 120 volts over here, because all our components are rated at 120 volts in this class. But when we do the transformer lab, you're going to hook it up for divide by 4. You're going to start off by dividing by 2, then you're going to hook it up by divide by 4, and you should see when you hook it up divide by 4, your secondary voltage is going to be 1/2 of what you measured when you divide by 2, right? You understand that? So we're going to hook up both of them because we're not hooking them up to loads. All we're trying to do is just see how the transformer works and learn how to jump it. But what's nice is that and I can tell real quick if the transformer's wired wrong, because when I look at the primary, there should be no crossing wires. Because notice none of these wires cross. We either put two on the 2 outside, or we put one on the center. Everybody okay? That makes sense? And that's the second lab we'll do. We're not going to hook up a circuit. We're going to hook up our transformer. And once we hook up our transformer, it's going to stay hooked up the whole semester long. So we'll end up using a divide by 2. So we're taking 240, which is not 240. We're getting 208, but it's good enough. We're taking a 240 and dividing it by 2 because all our components are rated at 120 volts. So we okay? Is everybody okay on how this thing's supposed to be wired? And we'll check it. So we'll start off hooking up the lab. We'll start off dividing by 2. And notice you're going to have to jump it. Y'all see the jumpers up there? I need to take them off. So you're going to jump your primary out. We're going to get we have 3-phase. We have 3-phase Y connection over here. A Y connection. It got that name because the transformers, they're drawn like this. And it's 3-phase. And this is where we get our 3-phase from. One of them's going to be labeled L1, one of them's going to be labeled L2, and one of them's going to be labeled L3. Now this gets very confusing because we have high voltage L1 and L2, and then over here we're going to call this what? L1 and L2. But this is a low voltage L1 and L2. This is high voltage, so don't get those confused with each other. In fact, I'll probably call them CL1 and CL2. And what they've done is they've got a fuse right here. And then in this right here, they're going to call this XF, because that's going to be the fuse size. So X1 goes to a fuse. Oops. So here's the secondary side. If I can get my camera back up. There we go. Focus it in. Oops, let me drop it down. I think it focused in real good when I got it down close in. Yeah, there we go. So here's X2. So X2, we're going to use that for L2. Here's X1 on this side of the fuse, but we're not going to use that one. We're going to use this one called XF. So it's on the other side. So XF, normally when we in a motor controls, we fuse the L1 side. So XF we're going to use for RL1, right? X2 we'll use for RL2. That makes sense? And then all our control circuits are going to hook on the bottom side. When we get to the motors are rated at 220, 208. So we'll have to run the motors directly off the 3-phase. But we'll, are we okay? You sure? So that's about as far as we can go. And they got all different types of transformers here. This shows how we jump for a divide by 1, right? Divide by 2. On ours, divide by 2. So ours is a divide by 2, and this would be divide by 4 for our transformer. And then we have multi-winding transformers. And that's all. We got multi-tap, so all different types of transformers out there. the one they got on the power pole, I don't know if they tap the primary or tap the secondary, but basically they have something like this, as they have three taps that they can hook to. And so when they bring it in, they hook it up, and what they're trying to do is they're trying to get what over here? 240. What we have on our house, we have what we call a center tap transformer. So up on the power pole, we have this. So we got a wire running here. So if everything was perfect, we would have 240 right here, across here. And then between here and the center, we would have what? 120. They take this and reference it to earth ground. So that's why you'll see two wires are insulated. That's the two outsides of the transformer. The ground, since ground is that's going to be a metal wire. That's your neutral coming down. So 240 basically is not referenced to ground. And then now we'll take the chassis on the outside and ground it. If the 240 is running like a water heater, we'll run a ground to the metal on the chassis. Anybody know why? Why do we want to ground these metal things? Because they're metal. We're using AC. AC creates a change in magnetic field. AC would induce a voltage into the metal. You understand that? So that means if you got we had a guy come in and says, well, I'm outside and it's been raining. Every time I touch my air conditioner, it shocks me. The metal on it. But what's he lost? He's lost his ground, right? Somehow the ground that's connected to that metal out there is gone. Because that's why we still hook a ground up to 240, even though 240 itself is not referenced to ground, right? You understand? We hook the what? We hook the metal up to ground, so that way, when it tries to induce a voltage into it, it can, because it can induce a voltage in the ground. So if you've got a hot water tank that's shocking you, it's not enough to kill you. First of all, another thing that we hook it up to ground for, if a hot lead shorts against the metal, it's going to pop your breaker or blow your fuse. If you don't do that, then that metal can also carry a true, not a induced charge, but it can carry a whatever that thing's rated at. So don't always run your grounds. My father-in-law hooked up his hot water heater, and he used the ground as one of his legs. So I said, TP, you can't do that. So his metal thing could actually carry a charge. So you have what we call a center tap transformer in there. So 120 would come across here, right? 120 and 240 across here. Questions? What time does class get over? 12, huh? 1:15. Okay, guys, let's take another break while I shift over to our next lecture. We're getting there. So what do y'all need? If you got your lab book, what do you need to bring Thursday? Bring your lab book, but if you don't have it, you should be okay. You need your lab book by next week. All we're going to do on Thursday at the end of class is we're going to let you decide who you want to partner with. We let you do that, and we can do two of one things. I can put a bunch of numbers in the hat and draw straws, right, and partner you that way, or you can choose your own partners. It's up to you. It's up to you. So we'll do that, and then we'll do our inventory part. It usually takes around an hour, hour and a half, so we need to make sure I give you all that much time to do the inventory. And then what we'll do Tuesday is we'll try Tuesday or Thursday, we'll do our first hands-on lab. And the first thing we're going to do is we're going to measure voltage inside the disconnect. We're going to hook up a transformer. We're going to wire it for low voltage. We're going to wire it for divide by 4 to start off with. Then we're going to divide by 2. We're going to measure the outputs to see the actual division ratios. Then we'll end up by hooking it back up to a divide by 4, because that's what we're going to use the rest of the semester. We're going to simulate a blown fuse. What I'll do is when you get to that section in the lab, I'll come over there and pull a fuse out of the disconnect. And then you'll see how you're going to measure to determine if the fuse is bad. And three phase is weird, and we'll have to talk about that too. So, okay, guys, I'll take a break. Let me switch over to the next lecture.